Okay, today we're talking about 18, which is just a continuation of yesterday. So yesterday we were talking about related rates problems. You had some relatively simple related rates problems assigned last night. There was a question about 18 just a moment ago when we talked about it. Is there another one that we had a question about? A surface area of what? Okay, surface area of a cube. Okay, so think about what surface area means. It means the area of all the sides. So with a cube, all the sides are the same shape. They're the shape of a square. So the area of one of them would be side squared, and since you've got 6 of them, that would be the surface area of a cube. 6 times s squared. Yes, that would be it. If you're talking about the surface area of a sphere, that's another one that seems to be common. It's 4 pi r squared. So those are just some things that, a lot of times these wind up being given to you if you need them, but you do need to commit some of the more basic ones to memory there.
What about number 11?
Which said, all right. So point, found the rate of change of the distance between the origin and a moving point on y equals x squared plus 1. The distance between the origin and a point on that there. Okay? So, we need, how do we find the distance between 2 points? Does anybody remember the distance formula for distance between 2 points? Yes, sir.
It's 16. Wait, the square root of x squared minus x minus x1 squared plus y minus y.
Yes. There's your 2 points. That's something called the distance formula that you probably learned back in Algebra 1 or Algebra 2. So that finds the distance between 2 points. And we're supposed to find the rate of change between the distance of 2 points when dx dt is 2. Okay. All right. Okay. So now, what are our 2 points? One's the origin. The other's a moving point. So we can just say that, let's say that second one back here is 0, 0, because that's the origin. Well, now this is simplified to the square root of x sub 2 squared plus y sub 2 squared, right? Yes, it looks very much like the Pythagorean theorem now, is what you should see. Very much like the Pythagorean theorem. So, but I see a potential problem here. I see 3 letters in here. D's, X's, and Y's. Is there any way that could be gotten down to 2 letters? It'd make our life so much easier if we could make it just 2 letters. You were told that y equals x squared plus 1, weren't you? So then we can make this d equals the square root of x squared, and I'm going to leave off the subscripts now since we've just got x's and y's, plus x squared plus 1 squared. And it said find the rate of change of the distance. So that's relatively simple now. We need to know what d of dt is, right? What other information were we given in the problem that we haven't done anything with yet? We know that dx over dt equals 2 centimeters per second. And that's all we know, right? So then we should be able to now take the derivative of this and plug this 2 centimeters per second in wherever we have a dx over dt. Our answer is just going to have x's in it in the end, okay? Because the left side of this becomes dd over dt equals 1/2 times this thing to the negative 1/2 times, what is that, 2x dx over dt plus 2 times x squared plus 1 times 2x dx over dt. This is chain rule. I'm bringing the 1/2 down, keeping the argument the same to the negative 1/2 power times the derivative of the inside. The derivative of x squared is 2x dx dt. The derivative of x squared plus 1 quantity squared is a chain rule again. 2 times that thing to the first power times the derivative of the inside thing, which is 2x dx dt. So you cannot get it to be completely clean, but you can. I'm not going to clean it up any more than that. You're smart people. All you have to do now is plug 2 in for dx dt and plug and chug for a while. That was number 11 on last night's fun activity. But now, as I said, the problems we were working, you may not think of them as easy, but were relatively easy in the sense that we have two variables. We had a volume and we had a side length, or we had a y and an x. We had x's and y's here. What happens when we get more than 2 things going on in there? Let's go back to the bicycle for a second, okay? On the bicycle, we've got the pedal that's turning that has a rate. We have the back wheel that has a rate, but then the bicycle also has a rate. So we might have to think of multiple things there. So some of these problems we're going to look at today, as we look at them, have more than one variable in there, or more than the 2 variables that we're accustomed to, such as this first one that we're looking at. The formula for the volume of a cone is 1/3 pi r squared h. Find the rate of change of the volume if dr dt is 2 inches per minute and h equals 3r. All right, so important information here is this volume formula. Dr dt is 2 inches and h equals 3r. Okay, what are we asked to find? The rate of change of the volume. So what are we looking to find here? Our answer is going to be dV over dt. So there's what we're looking to get to. Okay? Now we know that dr over dt equals 2 inches per minute, okay? And we know that h equals 3r. So, normal thing to do is we need to find a relationship between our variables. Well, we've got that. V equals 1/3 pi r squared h. What's the normal thing to do next? What did you do last night after you found your relationship? Take the derivative. What's the difficulty with taking the derivative of the right side? Okay, and the h. How are you going to take the derivative of the right side as it's written? You can, yes, and that's what we want to do. Because if we look at this right here, we've got 2 variables, r and h, that are being multiplied. How do we take a derivative when we have 2 things that are being multiplied? Product rule. First derivative, second derivative of first. So we'd have to go in here and just think out loud for a second. If we thought of this as the first, what's the derivative of h? If we say first times the derivative of second. What's the derivative of h with respect to time? 1 dH dt. Well, do we know anything about a dH dt anywhere in here? So we'd have to invent something to find that out. So what we would prefer to do in this problem is let's make this substitution right here to begin with. Okay? H is 3R. So now our formula changes to volume equals 1/3 pi r squared 3R. Now we've got just r's on the right side, so we can continue cleaning this up, and we get that the volume is pi r cubed. Now that we're down to just two variables, now's a happy time to take a derivative. Because if we were to take the derivative now, what do we get on the left side when we take the derivative? dV over dt. And what do we get on the right side? 3 pi r squared dr dt. Remember, we're taking the derivative with respect to time, so we have to have that dr dt in there. Now, we know what dr dt is, and the problem says it's dr dt is 2 inches. Does it say it's 2 inches sometime, most of the time? It doesn't say, so we will assume that it's all the time. So we can simplify this down even further to say that dV over dt is 3 pi r squared times 2, which is 6 pi r squared. That's what our dV over dt is. All right? So now the math of it becomes easy. A is when r is 6. So we put 6 in there. dV over dt is 6 pi 6 squared, which is 6 cubed, which is 216? 216 pi. What are the units going to be? It's dV over dt. So what is it? What should they be? Inches cubed, cubic inches per minute, right? Okay. How does squaring inches get us to cubic inches per minute? This 2 right here that we put into here, what were the units on that 2 there? Because that was a dr dt. It was already inches per minute. So this 6 pi that we're looking at right here, if we're thinking physics, if we're thinking units, that 6 pi was already in inches per minute. And then we put inches squared here, and that got us to inches cubed per minute. How do we feel about that? B part's not too hard, terribly difficult, is it? We're just going to put, instead of 6 squared in there, we're going to put 24 squared in there. And we just get a much more big number. Okay? Comfortable? Is that too hard? It's going to get harder no matter what. So. All right, so let's look at 22. A conical tank with vertex down is 10 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet. I just love these things. I just get excited reading these things here. So, first thing you need to do, draw a picture. What on earth does this look like? A conical tank. Like a cone. So we have a conical tank, something that looks like this. Okay? Now, what do we know? Vertex down, that means the pointy end's down. It's 10 feet across. That's 10 feet. And it's 12 feet down. Okay? Is that all right? Water is flowing into the tank at a rate of 10 cubic feet per minute. Tell me what 10 cubic feet per minute is. So, volume. Cubic feet is volume per minute. Means it's time, right? dV over dt. Are y'all okay with that? It's 10 cubic feet per minute. So that means that water's pouring into the tank at 10 cubic feet per minute. Now I want you to picture in your mind the tank's empty and you start putting water into it. What's going to start happening? It's going to start filling up. If I'm standing on the outside and looking at it, what am I going to see? It's going to look like it's going to start flying up. What's going to start happening the further up the tank the water goes? Why is it going to slow down? But you're right. It's going to look like it's slowing down, but is the same amount of water coming in? So it's just spreading out over a smaller area. So the rate that it's raising at is going to slow down the further up the tank we go. That's what we're asking. Find the rate of change of the depth when the water is 8 feet deep. So when we get to right along here, let's say that's 8 feet, we want to know if that is our height. We are trying to figure out what is dH over dt right there. Is dH dt different there than it would be down here at 4 feet? Do you think if we did this problem at 4 feet, would dH over dt be a different number? Yes. And at 2 feet, it'd be a different number. So it's always going to be a different number. So we need to know something about H. We know when H is 8 is what we've got over here. Can you figure out a relationship between volume and the height? The volume of a cone, if you look that up, is 1/3 pi r squared h. Just like the last problem. All right. Now, what's the difficulty with working with it just like that? We've got the r's and we've got the h's in there. Okay? Excellent, excellent, excellent. We've got to find a relationship. In the last problem, we were nice to you and we told you that H equals 3R. That's not the case over here. Can we come up with a relationship between these? Yes, we can. And I'm going to draw this up here as similar triangles, okay? I've got a triangle right here. And then I've got another triangle right here. And do y'all agree that those triangles are similar to one another? Okay. So what's the relationship between the triangles? Let's talk about the bigger triangle first. We've got 12 over 5. Now, where'd that 5 come from? Why do we take half of it? Yeah. Well, but why is that important to us? Yeah, but all right. Well, why didn't we just use the whole thing then? Why don't we just use 12 over 10? Why do you think I want to use 12 over 5? Creates a right angle. It's a triangle. But, I mean, if I do the big triangle, aren't they still triangles? Aren't they still similar? Why is it easier to use 12 over 5 instead of 12 over 10? What is 5? What is 5? What is 10 in this equation over here? There's no diameter in that program, right? 5 is a radius. 5 is a length of this green triangle, but it's also a radius over here. So we're better off to use something that we know is going to be in the problem. So 12 is to 5 as H is to what? Now, H is 8 at a specific time, but H is the height of the water at any given time. What's this little piece up here? What is this going to be whenever this is H? At 8, it might be 4, but I want to know what letter is it? What letter is this, would we use to represent this? R. 12, this distance right here, is to 5, this distance right here, as H, this distance right here, is to R, that distance right there. So that relationship is always going to be in play in this problem here. So if we do we want to solve this for H or for R? For R, okay. Why do you think we want to solve it for R?
You need to find the radius where the water is filled up.
Why do we want R to go away? Well, why don't we want H to go away then? We have H, but we're also looking for dH dt. So it's best to solve this green equation for R. And if you jump through the math there, you should find that R is 5/12 H. Okay? Now, that's not pretty, but that's the fact of what it is. Now, students always want to plug in this 8 right now and make that a nice number. You can't do that. You don't want to plug in this 8 into the problem until you have taken a derivative. So we're going to come over here now and we're going to say that the volume is 1/3 times pi times 5/12 H quantity squared times H. And yes, that's ugly to deal with, but you are intelligent beings and you can solve that out. So I want you to take about 2 minutes and find the derivative of that puppy right there. Derive both sides and come up with some type of something to look at. Yes, because you were putting it in place of R. So that's what I got when I got dV over dt. Is that what y'all got? Or have I moved too fast for you? Sounds like I've moved too fast. I'll give you another minute while I look for something over here. Okay, it doesn't do. Okay, so we get 3 times 25 pi over 432 h squared dh dt. What do we know now? Now we can plug stuff in. Do we know what dv over dt is? We do. It's 10. So we can plug in 10 here. We know what h is, don't we? 8 squared. And now it's just a matter of using our calculating device to figure out what dh over dt is. I have the utmost of confidence that you have the abilities to do that.
Can you not cancel off the 1/3 with the 3 when you do the derivative? So you would get 25 pi over 144 h squared?
Yes. I see what you're saying there. Yes, I see. When you did this down, you could have done that because 3 will go into both of those things there now. So yes, you could have done that. You could have simplified that more. Does everybody understand what she's saying there? If I had just left this 1/3 when I took the derivative, I would have wound up with just 25 pi over 144 here instead of that 3 times that. So you are correct. That would be simpler mathematics to work with there. But I'm going to assume that y'all can punch a calculating device and get to that answer there. Remember that on your calculating device, you've got to do all of that and divide 10 divided by all of that stuff. It's not 10 divided by 75 pi times h squared. You've got to do a division sign in either a parentheses with all of it or divided by for each one of them there. So just be careful with that and you should be fine with getting your answer there. Yes, sir?
I shouldn't know why the R is like the radius inbound.
Okay, let's go back because that's the hardest part here. The most difficult part of this problem is coming up with this relationship right here. 12 over 5 equals h over r. And that comes from the fact that when water starts going in, it's going to rise up, and as it rises up, it's going to fill out the entire area there. So if we look at from the center of the tank over, if we were to take a cross section right through here, that would look like a circle. And see, this distance from the center of the tank over would be the radius of the circle. So see, the radius is changing all the way up. The radius down here at the bottom is very small, and it gets to be 5 at the top there. So we know that 5 over 12, or 12 over 5 is the height of the whole tank divided by the radius of the whole tank. Then that means at any point within the tank, the height over the radius is going to be the same ratio because we've got the similar triangles there. Does that help? All right. Let's keep a look at a couple more problems here. A swimming pool, 12 meters long, 6 meters wide, 1 meter deep at the shallow end, and 3 meters deep at the deep end. Water is being pumped into the pool at a 1/4 cubic meter per minute, and there is 1 meter of water at the deep end of the pool. What percent of the pool is filled? At what rate is the water level rising? What do you think? I think I got a lot of problems and none of the ones that I wanted to, not the one that I wanted to look at today. We'll have to do that some other time. Swimming pool. There's a pretty picture of it over there. 12 meters long, 6 meters wide, 1 meter deep at the shallow end, and 3 meters deep at the deep end. Water is being pumped into the pool at that rate, and there's 1 meter of water at the deep end. All right, we're not going to worry about A part right now. We might come back to that in a minute, but B part, at what rate is the water level rising? So, who can tell me something? Can you read any of those numbers and say, I know what that is?
The 1/4 cubic meter per minute, the volume.
All right. It's not a volume. It's right. It is dV over dt. That's different than volume. Volume is how much is in there. This is saying how fast is it going in or going out? going in, so it's a positive number. 1/4 cubic feet per minute of water are flowing into the tank. All right? I'm going to give you what the pool looks like. If you could dig into the ground and look at it, okay? This is 1 meter right here. This is 3 meters right here. This is 12 meters right here. And then back in the wall is the 6 meters, okay? So where's our water at right now? It's 1 meter up here. So if we take this, it's about right there. Okay? So now, bless you. We need to know, it says, what rate is the water level rising? So what are we trying to find? If I said, when's the water level rising, what would you expect to see happening here for this to be rising? The green line's going to be going up. So the height, which of these numbers up here do you think defines the height of the water right now, or is related to the height of the water right now? The 3, the 12, or the 1? The 3, why not the 12 is kind of obvious, isn't it? Why not the 1? It's not up there yet. So we're talking about this is going up. So we're looking for a DH over DT. So we have a very simple problem. We need to figure out the relationship between Z and H. The volume equals 1/3 power squared H. I don't see a circle anywhere. Do y'all? That's the volume of a cone, but this isn't a cone, is it? Okay, so how do we find the volume of something? And you see, this is all water right here. So how can we find the volume of this water right here? Anybody remember how to do that? All right, let's show you what that's going to be. That volume is going to be 1/2 the base times the height times a different height. Okay? Now, I wrote it like that, so hopefully y'all will see something there. What does 1/2 BH look like? Y'all seen that formula before? Area of a triangle. Okay? Do you see a triangle anywhere here? Yes. We've got a triangle right here. Okay? We know that this part here is 1. So we've got this area. Now, what do you think this capital H is then? The total height, meaning what? 3 meters is when this gets on back up here. H is how many of these little triangles have we got stacked up all the way back? Remember, this is just a cut through. This is our capital H right here, the height of the whole figure. A formula that you may have been given somewhere along the way. Volume is base area times the height. So if I've got a cylinder, if I can find the area of the bottom, multiply it by times the height, that's the volume of the whole thing. Well, it might be called height, width. Is there really a difference between them? It's just a different name for it. Okay? So we know that this is 6 because that's how wide the whole thing is. So then, now, I have a question for you. Water's pouring into here, right? Water's already up to here. What would you call the base here? Is this 1 the base or is this green line the base? Doesn't matter. Which one do you want to call it? I think I'm going to call this the base, okay? Because remember, we're looking for DH, and this is going to be... So, Is the base, is that green line changing as water's pouring in here? Is the length of that green line changing? Is the height, H right there, changing? Is the height or width of this thing changing? No. Are y'all all in agreement with that now? Okay, I want to go back in time. When the pool's empty, nary drop in there. We cut the spigot on and water starts pouring in. Is the height changing then? Is the width, is this number changing when the pool is empty? Would you agree that it is? That's a totally different problem for us. It's a game changer, not a problem that we're qualified to solve right now, okay? So I just want to be sure you understand that this H is actually going to be a constant number. It's going to be the number 6 in here. So we've got volume equals 1/2 BH times 6, which we can go down and say that's the volume equals 3 BH. Now, we still have a problem. What's our problem? We've got 3 letters in there. So now, what is there a relationship between B and H? Okay, so tell me what it is. 12 is to 3 as B is to H. Can everybody see that? 12 is this distance from here to here. 3, ooh, is that distance there to there? It's 2. Oh, you're looking off into space or looking over there? Okay. All right, I was just curious. I first thought you just glazed over and were looking off into space and had all this writing in your head there. But okay, so it's 12 over 2. Now, why is it 2? I'm just asking the question. Why is it 2 from here to here? We said it was 3. We've got this 1 meter up here. Okay? Do you understand that? So that's the reason why it's only 2. 12 is to 2. B is this distance right here, which is in parallel to the 12. H is the distance that's parallel to the 2. So we've got, what, 12H equals 2B, or B equals 6H. Now, are we going to plug 6H in for B, or are we going to plug in 16B for H? Right, we're trying to find the derivative, and we're trying to find DH, so we want H's in our problem. So we can then say that the volume is 3 times 6H times H, 18H squared. Whew. We've done the hard part, now you can do the calculus. $36H is equal to 1/4, almost. Nope, not yet. Something's missing. 36H dH over dt. All right? Equal to 1/4. And we want to know about this when the height is what? 1. So we've got 1/4 equals 36 dH over dt. So we can find out that dH over dt is 1/144th inch per minute. It's rising 1/144th of an inch per minute. Yes. What did it say? Water's being pumped in, implying at this particular point when it was 1 meter. Because if it had been, is it going to be rising at the same level when it gets up here to 2 meters? No. Slower or faster? Slower, okay? Just like before, the further up the water goes, the slower it's going to seem to be rising then, okay? How do these seem? Does this seem hard? Does this seem easy? Does this seem confusing? Does this seem I don't care? Or
where did the H go? Yeah.
Okay, where did the H go right here? Remember, we put in 1 for it. Because remember, we were asked to find out what was happening when there's 1 meter of water at the deep end.
With the rate, the water level is
Oh,
rising
okay.
would be equivalent to 144H if you weren't looking at the 1 meter.
Yes, correct. Does everybody understand what she's saying? She said if we didn't know what H is, a generic form for this would be dH over dt equals 1 over 144 H inches per minute. Okay? So that's just a generic formula that you could use to find dH over dt for any given time in this problem here.
Well, you say like it's 1 meter of water deep end, so that means the height is 1 meter?
Yes, that means the height is 1 because there's 1 meter of water down here. So the height of the water is just 1. Now I have a question. What changes when we get to 2.5 feet? What happens when the water level gets up here? It stops being a triangle. It's going to rise at a steady rate from this 2 all the way up to this 3. Why? What changes once we get up here? Well, now we've got a rectangle. Now we don't have a triangle. Now we've got a length and a width. We've got a length of 12 and a width or a height of whatever here. Is the length changing any longer once we get up here? No. So now we've got a totally different problem from 2 meters to 3 meters. Totally different thing to have to deal with there. Well, we didn't ask about that, but I want you to recognize that that is a totally different animal to have to deal with there. All right, let's find one more to work with here. A trough, oil conical tank, we've already done one like that. I like that one. Construction worker. What do y'all want to work with? Do y'all want to do a construction worker pulling the plank up, or do y'all want to pull a boat in? Boat, all right. So we're going to the last one here, boating. A boat is pulled into a dock by means of a winch 12 feet above the deck. The winch, we're only focusing on a part. The winch pulls in rope at a rate of 4 feet per second. Determine the speed of the boat when there's 13 feet of rope out. What happens to the speed of the boat as it gets closer to the dock? Bless you. All right. What do you have? What do you have? What do you have? Do you see a relationship that you think we're going to be working with here? Or do you see a geometric figure or something we're going to be working with? Okay? So let's deal with this. We think we've got a triangle here, okay? 12, 13, and some other number we could figure out here. At this particular point, it has to be 5. But okay, but we've got a right triangle going on here, okay? So let's give some letters to these things here. What do you want to call this 13 line? A letter. Doesn't matter to me. C. All right, what do you want to call this line here? Okay, let's let that be B and let that be A, okay? So now, 4 feet per second. Is that a rate? Is it dA, dB, or dC? The winch pulls in rope at a rate of 4 feet per second. So it's dC over dt. Now, very important question. Is it positive or negative? Why? It's being pulled closer. Now, this is a very important thing for you to recognize here, class. What's happening to C? Is C getting shorter or longer? Shorter. Since C is getting shorter, DC has to be negative. Does that make sense? If C is getting shorter, DC has to be negative, okay? Determine the speed of the boat. That's another rate. Is that dA or dB? dA. So we're looking for dA over dt. All right? So now, what is the relationship between A and C? Okay, so we've got A squared plus B squared equals C squared. All right? So then we've done this enough to know that we get A over dA dt plus B over dB dt equals C over dC dt. All right, say that again now.
You know that the dB over dt is 0 constant, so it
Okay, she's saying this is constant. Okay, because the boat's 12, now yes, if we keep pulling on the rope forever, eventually we're going to be picking the boat up out of the water here. But when it's 13 feet out, we're not picking it up out of water. So B is constant, so dB is 0. So then we can simplify this to A dA over dt equals C dC over dt.
Maybe 2A, 2B.
Good question. I left out some numbers here, didn't I? Right. Yes, you're right that there should be a 2 in front of each one. But I just knew that they were going to cancel out, so I just threw them away. My apologies for causing confusion there. Well, I see that we've got 4 things, A, dA, C, and DC. We're looking for dA. We know DC is -4. C is 13. Determine the speed when there's 13 feet of rope out. So this is 13. We know A is 5. Tell me how we know A is 5. Special triangle. Did y'all learn that with Ms. Lehman in geometry, 5, 12, and 13, Pythagorean triples? Okay, you should have learned that this was going to be 5 right there. If you didn't learn it, how could you figure it out? A squared plus 12 squared equals 13 squared, and you work through that. Yeah, boom, boom. You get it that way. So now we can figure out then that dA over dt is -52 over 5, which is -10.4. Is this feet per second? Okay? Was that hard? Now, next question. What happens to the speed of the boat as it gets closer to the dock? So what's going to happen to dA as we get closer to the dock? What's going to change if we get closer to the dock? A and C are going to change. All right? So what's going to happen? Is it going to get faster or slower? And how can you figure that out? All right, let's change the values. What do you want to change the values to? So let's come over here. What do you want C to be? All right. Well, let C be 10. Can it be 10? If the height of this triangle is 12, can this line here ever be 10? No, it can't be. So it's got to be shorter than 13, but it can't be, let's say 12.5. Okay, I know that's an ugly number to work with. Let's say 12.5. Well, what's A going to be? How can we figure out what A is? Just like we did before, right? A squared plus 12 squared equals 12.5 squared. Somebody with a calculating device figure out what A is going to be for me. 3.5. So now we've got 3.5 dA equals 12.5 times negative 4. So what's dA this time? Negative 50 divided by 3.5. 4 would go into that 12 times. So that's going to be like negative 13 point something? Negative 14.2. So what happens as it gets closer? The boat speeds up. Is that a real life? What happens, or do you know? If you're pulling, have you ever been on the dock and start pulling a boat in? What happens what do you have to do the closer? That's right. And once it gets closer and closer, if you keep pulling with the same speed, what happens? That boat comes in and you crash and you bust the fiberglass and you've got to go fix it. So you have to slow down your pulling as you get closer and closer in. All right. What about B part? Suppose the boat is moving at a constant rate of 4 feet per second. Determine the speed at which the winch pulls in the rope, and there is a total of 13 feet of rope out. What is B changing? What changes in B? Right. In B part, dA over dt, is it positive 4 or negative 4? It's negative 4. Okay? So the only thing that's going to change is down here for B part. Instead of this being negative 4 right here, it's going to be a negative 4 over there. So we're figuring out a little different there. So the math of it doesn't change a whole lot there. Okay, the bell's about to ring. My goal, I'm amending assignments for the week, okay? My goal is for you to turn in homework 17, before you leave tomorrow, okay? Now, tomorrow we've got to talk about something totally unrelated to this stuff here. When we come back next week, we'll pick up with related rates again. We'll talk about a couple of these problems that we didn't do today. I'm going to pull out my most favorite problem, and we'll work it on next Tuesday. Then you can work on homework 18. Then you can work on your project. Then you can work on your WebAssign and all that stuff. So your assignments for this week have been amended to only homework 17 and the 3 FRQs. Okay? I'll make those changes in Shobi and on RenWeb and on Moodle. Yes. This will be